Why is 1 quadrillion and range 1 quadrillion 1 so fast in Python 3? It is my understanding that the range function, which is actually an object type in Python 3, generates its contents on the fly, similar to a generator. This being the case, I would have expected the following line to take an inordinate amount of time because, in order to determine whether 1 quadrillion is in the range, a quadrillion values would have to be generated. Furthermore, it seems that no matter how many zeros I add on, the calculation more or less takes the same amount of time, basically instantaneous. I have also tried things like this, but the calculation is still almost instant. If I try to implement my own range function, the result is not so nice. What is the range object doing under the hood that makes it so fast? Martijn Peters' answer was chosen for its completeness, but also see Abernert's first answer for a good discussion of what it means for range to be a full-fledged sequence in Python 3. And some information/warning regarding potential inconsistency for _contains _function optimization across Python implementations. Abernert's other answer goes into some more detail and provides links for those interested in the history behind the optimization in Python 3, and lack of optimization of string in Python 2. Answers by Poke and by Vint provide the relevant C source code and explanations for those who are interested.
The Python 3 range object doesn't produce numbers immediately. It is a smart sequence object that produces numbers on demand. All it contains is your start, stop and step values. Then as you iterate over the object, the next integer is calculated each iteration. The object also implements the object._contains_hook and calculates if your number is part of its range. Calculating is a near constant time operation. There is never a need to scan through all possible integers in the range. From the range object documentation. The advantage of the range type over a regular list or tuple is that a range object will always take the same, small, amount of memory, no matter the size of the range it represents, as it only stores the start, stop and step values, calculating individual items and subranges as needed. So at a minimum, your range object would do. This is still missing several things that a real range supports, such as the .index or .count methods, hashing, equality testing, or slicing, but should give you an idea. I also simplified the _contains_ implementation to only focus on integer tests. If you give a real range object a non-integer value, including subclasses of it, a slow scan is initiated to see if there is a match, just as if you use a containment test against a list of all the contained values. This was done to continue to support other numeric types that just happen to support equality testing with integers but are not expected to support integer arithmetic as well. See the original Python issue that implemented the containment test. Near constant time because Python integers are unbounded and so math operations also grow in time as n grows, making this O log n operation. Since it's all executed in optimized C code and Python stores integer values in 30-bit chunks, you'd run out of memory before you saw any performance impact due to the size of the integers involved here.
The fundamental misunderstanding here is in thinking that range is a generator. It's not. In fact, it's not any kind of iterator. You can tell this pretty easily. If it were a generator, iterating it once would exhaust it. What range actually is a sequence, just like a list. You can even test this. This means it has to follow all the rules of being a sequence. The difference between a range and a list is that a range is a lazy or dynamic sequence. It doesn't remember all of its values, it just remembers its start, stop, and step, and creates the values on demand on _getItem_. As a side note, if you print iter a, you'll notice that range uses the same list iterator type as list. How does that work? A list iterator doesn't use anything special about list except for the fact that it provides a C implementation of _getItem_, so it works fine for range too. Now, there's nothing that says that sequence._contains underscore has to be constant time. In fact, for obvious examples of sequences like list, it isn't. But there's nothing that says it can't be. And it's easier to implement range._contains underscore to just check it mathematically, val, start, %step, but with some extra complexity to deal with negative steps, than to actually generate and test all the values, so why shouldn't it do it the better way? But there doesn't seem to be anything in the language that guarantees this will happen. As Ashwini Chaudhary points out, if you give it a non-integral value, instead of converting to integer and doing the mathematical test, it will fall back to iterating all the values and comparing them one by one. And just because Python 3.2 Plus and PyP3.x versions happen to contain this optimization, and it's an obvious good idea and easy to do, there's no reason that IronPython or new Kickass Python 3.x couldn't leave it out. And in fact, Python 3.0 to 3.1 didn't include it. If range actually were a generator, like my _crappy_range, then it wouldn't make sense to test _contains _ this way, or at least the way it makes sense wouldn't be obvious. If you'd already iterated the first 3 values, is 1 still in the generator? Should testing for 1 cause it to iterate and consume all the values up to 1, or up to the first value is greater than or equal to 1?
Use the source, Luke. In Python, range ... contains _, a method wrapper, will eventually delegate to a simple calculation which checks if the value can possibly be in the range. The reason for the speed here is we're using mathematical reasoning about the bounds, rather than a direct iteration of the range object. To explain the logic used, check that the number is between start and stop, and check that the stride value doesn't step over our number. For example, 994 is in range 4, 1002, because 4 is lower than or equal to 994 is lower than 1000, and 994 to 4, %2 equals 0. The full C code is included below, which is a bit more verbose because of memory management and reference counting details, but the basic idea is there. The meat of the idea is mentioned in the comment lines. As a final note, look at the range underscore contains function at the bottom of the code snippet. If the exact type check fails, then we don't use the clever algorithm described, instead falling back to a dumb iteration search of the range using underscore psequence underscore iter search. You can check this behavior in the interpreter. I'm using v3.5.0 here.
To add to Martine's answer, this is the relevant part of the source, in C, as the range object is written in native code. So for pylong objects, which isn't in Python 3, it will use the range underscore contains underscore long function to determine the result. And that function essentially checks if ob is in the specified range, although it looks a bit more complex in C. If it's not an int object, it falls back to iterating until it finds the value, or not. The whole logic could be translated to pseudo-Python like this.
If you want to see more, please consider subscribing.